Hi, everyone. So this is the replacement lecture for November 1st. So okay, so where did we leave off last lecture? So our goal is to prove the following theorem. We want to show that there exists a unique multilinear alternating and normalized function d from f to the n by n to f called the determinant. Okay, and at the end of lecture last time, we also gave the following definition, just to remind you. So we defined a function called det from fn by n to f. So taking a matrix A and sending this to the following element of f. So we're going to take a sum over all permutations sigma of n elements. We're going to take the sign of sigma, SGN, and then we're taking the product as I goes from 1 to n of the matrix A, and we're looking at the entry in the ith row and sigma of I column. Okay, and we worked out a few examples of how this would look when n equals 2 and when n equals 3. Okay, so what do we need to do to prove the theorem? So how this is going to go is I'm going to first show that det, this function defined above, is multilinear alternating and normalized. And then part 2, given any multilinear alternating and normalized function d, we have that, in fact, d must be equal to det. And this will prove the uniqueness part of the theorem statement. Okay, so in the last lecture, we did both of these steps for the 2x2 determinant. And so now we're going to do the full proof for the general case. Okay, so let's start with part 1. So I'm just going to move part 2 away so we have room. Okay, so let's start with proving that it is multilinear. So I'm going to break this down into two steps. I'm first just going to show that if I have in one coordinate lambda times a vector, then I can pull out the lambda. And then the second thing is that I'm going to show that if I have a sum of two vectors in one coordinate, then I can break up the determinant across that sum. So let's first do it for lambda. So let's say I'm taking det of v1 up to, let's say, lambda vk up to vn. Okay, then just applying the definition. So I'm going to think of the v's as being the columns of the matrix. Okay, so just taking the definition of the determinant, this is going to be the sum over sigmas in Sn, Sgn of sigma, and then I have a product as I goes from 1 to n. Okay, so I want the ith row of this matrix. So I'm going to take the ith row and the sigma of ith column. So that will correspond to taking v sub sigma of I. Okay, and then we're looking at the ith entry of v. So I'll write that like that. So this is the ith entry of the vector v sub sigma of I. And okay, so what I've written here isn't quite right, because in the kth coordinate, we don't just have the vector v sub k, we have lambda times v sub k. So I'm going to write here, this is going to be for all i's not equal to k, and then we're also multiplying by k times okay. So we don't want the kth vector v, so I want that sigma of I is not equal to k. Okay, so I'm producting over those indices I such that sigma of k is not equal to I. So what is represented in this product is all of the vectors other than vk. Okay, and then off to the side, we're also going to multiply by lambda times v sigma of I sub k. Nope, this is wrong. Okay, so sorry. We know that sigma of I is equal to k, and then we want the ith we want whichever I produced yeah, okay, so we want the whichever number. So what, yeah, okay, so what goes here? This is the number, let's say j, such that sigma of j is equal to k. So this will be sigma of j. Where j is the number such that sigma of j is equal to k. Okay, so j is exactly the index that was left out of this product. Okay, That was a little bit cumbersome to write out, but it's not so bad. So we can rewrite this as the sigma in Sn. And actually, so this lambda is independent of any of these sigmas, right? So I can fully pull out the lambda from this sum. So this is going to be lambda times this sum, SGN sigma times, okay, well now I'm able to group all of these things into one product because now I am truly just looking at the vectors vk. There's no scalar multiples. So this will be the product as I goes from 1 to n, v sigma I sub I. Okay, but then this part is exactly just the determinant of the v1 up to vn. So this is lambda times determinant of v1 up to, we'll have just vk in that coordinate, up to vn. Okay, so that proves one part of the multilinearity. We can pull out scalars. What is the second part? Okay, we need to move this again. We're going to need to move this a lot. I'm just going to put it on a different page completely. Okay, so now we need to show what happens when we have a sum in one coordinate. So let's look at det of v1 up to, and now we'll put vk plus wk in this coordinate up to vn. Okay. So this is going to be equal to, just by the definition, the sum over sigmas in Sn, SGN of sigma. Okay, now again, we're going to be looking at a product of entries of these guys, and we're going to have something different happening in one of these entries. So I'll take again the product as I goes from 1 to n, and we're looking at those i's such that sigma of I is not equal to k, and we'll have v sigma I sub I. And then we're also going to be multiplying this by whatever's happening in this column. So that will give us vk plus wk, and we want the sigma jth entry. Oops, okay, I'm realizing that there's again a mistake in the above. So this is just the jth entry of this, right? Because we know that sigma of j is equal to k. So we want this to be j. Okay, so again, here we have j is the index such that sigma of j is equal to k. Okay, and then I'm gonna just break this up into two separate sums. So I'll do this in a few steps. So I'll have the sum as sigma goes over Sn. And then, okay, so this is just the product of a bunch of numbers times the sum of two things. So I can distribute. So for one part of this, I'll have SGN sigma, and then the VK term I can lump in with the other V's. So I'll have the product as I goes from 1 to n, V sigma of I, and we want the ith the ith entry of that. And then I get plus SGN sigma times the product as I goes from 1 to n, and I is not equal to j. I need to scoot all this over a bit. And this is going to be V sigma I sub I, and then times W K J. Okay, but then I can, so this is like right now it's one big sum. I can break it up as two sums. So I'll have sigma, sum over sigma and Sn. And that will just be of the first part. And then plus sigma and Sn of the second part. Okay, but then what do we see? This is the determinant of the V's plus the determinant of mostly V's, but in the kth coordinate we have W. So this is det V1 up to, and then in that coordinate we'll have VK up to Vn plus the determinant of V1 up to WK up to W or Vn. Okay, so that was the other half of what we needed to show for multilinearity. So yeah, we showed that we can break it up across sums, and we can take out scalar multiples, and together those would give you the full multilinearity property. Okay, so going back, so we proved multilinear. We also need to show alternating. So for this one, we need to show that if we have repeated vectors, then we will get that the determinant is 0. So let's take the determinant of V1 up to Vk, up to Vj, up to Vn, where, so let's assume that Vk is equal to Vj. Okay, so let's write this out. So this is going to be the sum over sigma and Sn sine sigma times the product as I goes from 1 to n, V sigma I, and we want the ith coordinate of that. Okay. So what happens? Let's say I have some permutation of the numbers 1 up to n. So let's let sigma be a permutation. And let's let sigma prime be the permutation obtained from sigma by transposing the things in the kth and the jth positions. Okay, so let's do an example. So if sigma is the permutation 2, 3, 1, 5, 4, and let's say this is J and this is K, then sigma prime would be 2, 4, 1, 5, 3. Okay, so we just switched 4 and 3. Okay, so I make the following claim. My claim is that SGN of sigma is the opposite of SGN of sigma prime. Okay, I think that this is clear because let's say, whether or not sigma is even or odd, sigma prime is obtained from sigma by doing one additional transposition. So sigma prime will have the opposite sign from sigma. Okay, so I think that that's clear. My second claim is that this part of the determinant corresponding to sigma and sigma prime is equal. So how would I write that? So I'm going to say product as I goes from 1 to n, v sigma I, this is equal to the product as I goes from 1 to n, v sigma prime of I sub I. Okay, so why is that? Aside from J and K, we're going to be multiplying the same numbers for sigma and for sigma prime. And then for the numbers J and K, so we would have different, one of them, so say in this example, one of them would have a 3 here and the other one would have a 4 here. But since these two vectors are the same, we'll end up with the same number in that entry. Okay, so the contributions corresponding to those two permutations to the determinant are equal. Okay, and the last thing is that that we can basically pair every element in Sn with its corresponding sigma prime. So every element in Sn is paired up. So maybe I'll make a quick argument as to why. So let's look at the set of sigmas in Sn such that sigma of J, oops, I switched J and K between here and here. So let's make this consistent. I'll just call that one K and that one J. Okay, so let's look at the sigmas in Sn such that sigma of K is less than sigma of J. Okay, so for example, this one would be an element of this set, and this one would not be an element of the set. And then we can also look at the set of permutations in Sn such that sigma of K is greater than sigma of J. Okay, so in this example, sigma prime would be in this set, and sigma is not in that set. Okay, so let's call this I'll call this M and this one M prime. Okay, so my claim is that the map sending the function P from M to M prime, sending an element sigma in M to the element sigma prime of M, just obtained by switching the jth and the kth elements, this is a bijection. Okay, so you can check this, you can prove it if you like, or you can check it in an example. But the upshot of this is, okay, so what is this going to do here? So let's continue with this calculation. Just copy it again. We need more space once more. So I'm going to break up this sum into sigmas in M. Or no, I'm going to do it this way. Okay, so we're going to look, I'm going to do sigmas in M. Okay, so I'm going to group the terms of this sum according to the pairs sigma and sigma prime. So this is going to be SGN of sigma times the product as I goes from 1 to n, V sigma I sub I. Okay, and then we're going to group that with the corresponding term from sigma prime. So we'll have SGN sigma prime product as I goes from 1 to n. Scooch this over. V sigma prime of I J. Okay, great. And like we talked about, the two contributions here are going to be equal for sigma and sigma prime, and the signs are going to be opposite. So we get the sum over sigma in M, SGN sigma, product as I goes from 1 to n, V sigma I sub I, minus SGN sigma, product as I goes from 1 to n, V sigma I sub I. Okay, so these two terms cancel each other, and we just end up with, we're adding up a bunch of zeros. So we sum over sigma and M of 0, which gives me 0. Okay, so that tells me that det is alternating. Okay, so let's go back. We need alternating and we need normalized. Okay, normalized is the easiest one, so we've already done all the hard work. So now we do normalized. So let's take det of E1 up to En. Okay, so this is going to be sum over sigmas in Sn, Sgn of sigma times the product as I goes from 1 to n, E sigma I sub I. Okay, so here's the thing. These vectors E sub I are filled with a lot of zeros. So a lot of these, the terms in this product are going to be 0. And if we ever even have 1 0 term in the product, then the whole thing is 0. So when is this not 0? So this is only non-zero. So E sub I is non-zero in the ith coordinate. So this is only non-zero when sigma of I is equal to I. And we need that to be true for all I in order to get a non-zero term. Okay, so what does this mean? Only the identity permutation gives me a non-zero summand. So let's see. So we get most of the terms are zero. So and then we get one. So these are all non-identity permutations. And then we get some contribution from the identity permutation. So the one where sigma of I equals I as I goes from 1 up to n. So let's calculate what that is. Well, the sign of that permutation is 1 because we don't have to do any transpositions. So we get 1 times the product as I goes from 1 to n. And we're going to be looking at E sub I comma I. So like we said, E sub I is equal to 1 in the ith coordinates. This is going to be a product of a bunch of ones. So overall, we get 1. Okay, so let me just like draw a picture for this because I think that might be useful. So we're filling a matrix with the standard basis. So we get a matrix with ones on the diagonal like this. And then every term in the determinant corresponds to picking so we're going to pick something in the first column. We have to pick something in the second column that such that we're not in the same row as any of our previous selections. So then in the last column, we have to pick this. If you're familiar with chess, then what this is like we have to place 3 rooks inside of this matrix such that none of them can attack each other. Another way to think of this is, you know, this rook can look this way and look this way, and it should see nobody else. And similarly, this one looks this way and it looks this way. It can only look in straight lines. It doesn't see anything else. And same with this one. Okay, so the determinant is summing over all ways to do this. And in this case of looking at the standard basis, we need to have, we're going to get zeros unless we just pick these to be the rooks. Okay, like the diagonal is the only way to get something that's non-zero when we product these together. Okay, so that's why this is normalized. Okay, so let's go back to our proof map. So we've now proved normalized. Then we had step 2, which was to show that this was the unique function that accomplished this. So let's go to step 2. So given any multilinear alternating normalized function D, we're going to show that D is equal to the determinant. Okay, so this is very similar to what we did in the 2x2 and the 3x3 case. So we calculated what D of A, B, C, D needed to be just using the properties. And that's what we're going to do again, but we're doing the n by n case, so it's going to be a little bit more complicated. Okay, so let's say I want to compute D of the vectors v1 up to vn, right? Because I can feed this function any choice of n vectors. Okay. So what I need to do is rewrite each of these vectors in terms of the standard basis. Okay, so let's say v1 is written as a linear combination as follows. So I'll call this v11 e1 plus da 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 up to v1n en. Okay, so this is just like, what are these v11 up to v1n? This is the coefficients needed in order to write v1 as a linear combination of the standard basis vectors. Okay, and we're going to do that in every coordinate. Okay, so there it is. Okay, so now I'm going to do the multilinearity step. So this is going to be a little bit confusing. So for multilinearity, I'm going to start by just breaking this up across the sums. So what can I do? I need to, given any choice of one of these, any choice of one of these, and so on, I'll get a term. So, I could pick the first summand in every coordinate, and that would give me a term of the determinant, for example. So I'm going to take the sum as indices I1 up to, of course, a lot of these are going to end up being 0. So we'll say which ones are 0. So I'm going to let all of these indices, I1 up to In, range from 1 to n. Okay, and then the corresponding term will be D of V sub. Okay, so in the first coordinate, I'm going to have, okay, so it's always going to be, here's what it's going to be. V something. No. Okay, this is tricky. So, okay, yeah, so in the first coordinate of this, I'm going to have a selection of one of these, right? So the subscript on V will always start with 1 here. So it's going to be V1 something, and that something is specified to me by my selection of what I1 is. Okay, so this is V1 I1 E I1. Okay. And let's write the second coordinate just to be super clear. So in the second coordinate, I'll have V2 I2 E I2 and so on. V N I N E I N. Okay, so in this step, I've just done like the additivity part of multilinearity. And instead of doing it step by step, like one step for each coordinate, I just wrote what you would get after applying this in every coordinate. So in each coordinate. So going back to the 3x3 case, this is our 27 terms. Okay, but a lot of those 27 terms are going to be 0. So it's 0 whenever I have duplicate selections of e's. So what I need is that, so we're going to have 0 unless the map 1 goes to I1, 2 goes to I2, and so on up to n goes to in, unless this map is a bijection. Right? Because if it's not a bijection, then 2 of these i's will be equal, and then I'll have the same e sub I appearing twice in this determinant. Oh shoot, I meant to I'm going to pull out the coefficients now as well. So this is like applying the homogeneity part of multilinearity. So I'm going to just pull out all of the v's. So this will be the sum as I1 up to in, range from 1 up to n. And I get a product of, let's say, as j goes from 1 up to n, and this is going to be v j I j. Whoa, maybe I should call this k so it's clearer. Okay, so we're going to product as k goes from 1 up to n, and it'll be vk I k. Okay, so we're pulling out all of the coefficients, and then we have d of the e's. So e I1 to e in. Sorry about that. Okay, so now this thing is going to be 0 unless I've selected a distinct choice of standard basis vectors. So I need that this is a bijection. Okay, this step is let's call it the homogeneity part of multilinearity. And then this part is by alternating. Okay, so what that means is we can rewrite this as the sum over sigmas in Sn, because all permutations will appear in this sum, because a priori we're just summing over all possible choices of I1 up to In. So we'll get those sigmas. We're going to have the product as k goes from 1 up to n, v k sigma of k and then we're taking the d of e sigma of 1 up to e sigma of n. Okay. Now we know that what does this come out to? This is just going to be the sign of the permutation, because we just need to do some number of switches to get this back to the standard basis in the correct order. So this is going to be the sum over sigmas in Sn times this product. Vk sigma of k, whoa, that's a subscript. Okay, vk sigma of k and then SGN of sigma, and then D of the standard basis. Okay, so then this is like from here to here. This is by the thing that we proved, that switching entries multiplies by -1, by that property that we proved a couple of days ago. Okay, and then by the normalized property, we know that this is equal to 1. So then this whole thing comes out to the sum over sigma in Sn, SGN of sigma, times the product as k equals 1 up to n, vk sigma of k. Okay, so okay, so what is left? I need to so what is the actual definition of the determinant? I need that this is equal to the sum over sigmas in Sn sine sigma, the product as k goes from 1 up to n, and I want okay, so I think just the way that I named these, the indices were maybe switched from what it would have been the easiest thing to name them as. So, okay, so let's look back at this. So I want to think of this as a matrix whose columns are the V's. So then the determinant will look at the ith row and the sigma of ith column. So I'll take the sigma of ith, or in this case we chose k, sigma of kth v, and I'm looking at the kth entry of that. And is that equal to what I called vk sigma? So if I took so let's see, for example, this is V. Okay, so the coefficients, okay, so this is my claim. The coefficients that I've written here make a matrix whose rows are the V's. Okay, so let me compare this matrix to the matrix with the coefficients that I've written. So this would be V11 up to V1n, Vn1 up to Vnn. So, okay, so let's compare these two matrices. So these are the coefficients that I defined here. And this is like the matrix that we're taking the determinant of. So so I think that this means that we're all good, because what this is telling me is that V sub k comma sigma is equal to the kth entry of the sigma kth vector, which is what we want here. Let me just think that through again. So V k sigma k is the sigma kth wait, now I think I have it wrong. Let me just run back through this. So VK sigma K is, we'd be looking at the kth vector V sigma kth entry. Okay, so what have we shown? Let's rectify this problem. So this is the determinant. This is equal to det of the matrix where I have the V's as rows. Okay, but to prove uniqueness, what I want is that this is actually equal to the determinant where I have, so this is what I want, that this is equal to the determinant when I have the V's as the columns. So it turns out that this is true. So let me just state a fact. So let's define the transpose of a matrix. So let's say I have a matrix A with entries A, 1, 1, up to AN1 up to A1N, ANN. Okay, then A transpose basically just switches the roles of the two indices. So this would be in my original matrix, so the diagonals stay the same, but now I would have A1N here and AN1 here. Okay, and my claim is that the determinant of A is equal to the determinant of A transpose. I think this might be a problem set or a recitation problem. Let me see. I'm not sure, but my hint is, so let's go back to here. So here's my hint as to how to work this out. Since a permutation is a bijection, it has an inverse. So sigma has an inverse. Okay, so we could rewrite this as okay, I don't want to use any more time where I'm just staring at this and thinking. So I will sort this out on my own and post a comment about it. And thanks for watching this this recorded lecture, and I will see you all on Friday. And sorry about the difficulties here at the end, but so how does the proof wrap up? We're down to this fact. So the determinant is unique up to, okay, wait, maybe I don't need to prove anything because here we go. So, okay, here's the proof. So we showed that if we have, so here's like the logic. If we have a multilinear alternating normalized function, then it equals det of A transpose. Okay, so this is the function. It sends a matrix A to the determinant of the transpose of that matrix. We also showed that the determinant was such a function. So showed the determinant is a multi-alternating normalized function. So by the first point, it must also equal this function. So det of A is equal to det of A transpose. And furthermore, any such function, any function satisfying this is equal to this, so it is unique. Okay, so that got a little bit confusing there at the end with the transposes, but this is how we finish the proof at hand. And then if you wanted to prove directly that this fact holds, that is also possible, just from the formula for the determinant. Okay, so I will see you all on Friday, and thanks for watching.